In this video, I will share with you some of the key technical details associated with the Abaqus technology brief on the simulation of ballistic perforation of aluminum plates with Abaqus Explicit. Let's start with a quick look at animations of the simulation results. While the geometry and initial conditions for this model are relatively simple, it is the sophisticated material model that is the key to the success of this simulation, which matches published experimental results. The Abaqus material models that make this simulation work are the Migra-Nielsen equation of state for modeling materials at high pressure, the Johnson-Cook plasticity model that accounts for strain rate and thermal effects in the material and its compressibility, the Johnson-Cook dynamic failure model to define the Abaqus ductile damage initiation criterion, and the Abaqus progressive damage framework. Next, I will give you a guided tour of the Abaqus CAE model. The model consists of two parts, the projectile and the target. The projectile is an ogive node steel rod approximately 9 centimeters long. The target is a 26 millimeter thick square aluminum plate. Let's take a closer look at the steel material. In the material editor, you can see the list of material behaviors, which have been defined using SI units. In this simulation, we expect that the pressure generated by shock wave propagation will exceed the material strength by several orders of magnitude. So we can assume that initially the material behaves hydrodynamically, and strength effects appear later. Consequently, for both materials, the volumetric behavior is described by the Migra-Nielsen equation of state, while the deviatoric behavior is simulated using the linear elastic and the Johnson-Cook plasticity models. Generic parameter values for both the Johnson-Cook and the EOS material were taken from a Lawrence Livermore National Laboratory report. While these values are close to the materials used in the simulation, some of the parameter values had to be calibrated to match the true stress-strain experimental data for the aluminum target and steel projectile. The EOS model requires reference density, Migra-Nielsen coefficient, and C0 and S, which define the linear relationship between the shock velocity and the particle velocity. The Johnson-Cook plasticity model, which is an incremental elastic plastic rate model that accounts for strain rate and thermal effects, requires the yield stress, hardening constant, hardening exponent, the melting and transition temperatures, and the thermal softening exponent. These parameters define the plastic hardening, while parameters C and epsilon.0 define the rate dependence. Defining specific heat, along with an initial temperature field, allows for the inclusion of adiabatic heating due to plastic dissipation during the analysis. To simulate failure, the Johnson-Cook dynamic failure model is used. The Johnson-Cook failure parameters were taken directly from the literature, except that the sign of the failure parameter D3 has been reversed, because the Abaqus implementation of the Johnson-Cook damage model requires a positive value for this parameter. Damage evolution has been defined, and elements are deleted by default upon reaching the maximum degradation. Let's take a quick look at the contact definition. General contact is used to define the interaction between the projectile and the target using a pair of surfaces that include both the external and internal element faces, thereby ensuring that contact will be enforced as the target erodes. Frictionless contact is used. Now that you have seen the model, let's return to the results. The simulated time-resolved motion is in good agreement with experimental X-ray photographs. For the normal impact, the projectile remains undeformed. During the oblique impact, the projectile shank undergoes visible bending while its nose remains undeformed. Note that the hourglass stiffness of the projectile had to be increased to prevent excessive nose deformation. In this plot of the projectile's residual or exit velocity versus striking velocity for normal impacts, you can see the close agreement between the experimental and simulated residual velocities for a wide range of striking velocities. In the equivalent plot for the oblique impact case, the numerical and experimental results for lower striking velocities are farther apart than for the normal impact case, but in general, there is still good agreement between the simulation and experimental results. Thank you for your attention. For more details regarding this simulation, please refer to the associated technology brief.